My name is Yannis, and I'm happy to be here, so I can just be here for one day. It's a pity, but at least I am here. And I would like to talk first about R-GIS bridges for statistical geocomputing. Has anybody of you already used R-GIS bridges? Or do you know what I mean by R-GIS bridges? There's one. Nobody else? Yeah, I knew. Tim also, very good. Chris, excellent. So, but the rest of you never heard of RSAGA or R-GIS 7 or RQGIS? So what we are going to do today is we would like to access GIS functionality from within R. And before we do that, I will introduce myself, and then I will give a little pep talk why this is a good idea, because frequently people ask, when does R finally become a GIS? And well, aside from the fact that it already is a GIS, it is not necessary that it has to become a full GIS, because you can access the GIS algorithms from within R, so by duplicate them. Just use what is out there, especially if you have in mind that software packages like GRASS or QGIS or SAGA are really well supported and have a large community working on them. So why duplicate it? Just use this stuff. Okay. This is the same repository Robin has used. So you find it on the geocomp R geostats_18. And yeah, let me first introduce myself. I started out as a geographer, in fact doing landslide modeling, so landslide susceptibility maps in southern Ecuador, and then I moved a little bit further to the west, to northern Peru, and there I was mainly interested in vegetation, how the floristic composition changes with El Nino. And yeah, this is where I was. And there's also here a nice picture of a cactus living on a Loma mountain. We will use this use case today for modeling the floristic gradient. It's really a fascinating vegetation, but I will tell you a bit more about it later on, and then we can do nice spatial prediction maps. Yeah, then I worked also at GFK geomarketing, so as a geodata scientist, and this was also very interesting because there I have realized how you can apply all the methods used, for example, in ecology or geomorphology in business, and it's just the same from a point of methods at least. So if you model the floristic gradient or biodiversity, it's just the same as modeling purchasing power or whatever, services, whatever you want. But then El Nino came, and this brought me back to academia, because this was what I actually wanted to investigate during my PhD study, but I waited in vain for, I don't know, 4, 5, 6 years, never occurred, and then in 2017, there it was. And this is how it looks like in normal years, and this is when the desert is blooming. So from a complete desert interspersed by a few shrubs, suddenly you have a tree or grass tree savanna. Good, but now let's talk a little bit about R-GIS bridges. I think you all have noted that you can use R as a GIS, and you have learned about the SF package, or maybe also about the SP package on Monday, I guess. Robin today told you a bit about the tidyverse and how you can combine vector processing with this stuff in R. And I think you already are aware of the raster package as well. So we have the two main data models, vector model and raster model. We can display them in R, and we can handle them in R. We can compute stuff with them. So this is what a GIS is. And in fact, at the moment, there are more than 100 geo-related R packages. And the R-Goodall package is for importing and exporting spatial data, and it's supporting hundreds of different data formats. In fact, almost any GIS software is using this Goodall in the background for importing and exporting spatial data. And yeah, SP and SF, the raster package, And Tim has told you about the MapView package, also really great for interactive map handling. So if you just want to have a quick glance at your own data, you don't have to do this in the GIS. You can do so now in R as well. So defining a GIS as a system for the analysis, manipulation, and visualization of geographical data, we can say R has become a GIS. This is the Longley et al. Definition of a GIS. Good, but there are a few things GIS systems are able to do, such as digitizing. Okay, Tim has created the map edit package, but if you have to digitize, I don't know, hundreds of points, or if you have to do rivers or street networks or whatever, then maybe it is a better idea to do it in a GIS software, because there you have the tools. R is not a spatial database, so you can access spatial databases from within R. We won't talk about this today, but it is also possible. And R is a spaghetti GIS, so it doesn't support topology. And if you need topology or topological functions, then you can access them from within R. And my first approach would be to use GRASS and then R-GRASS 7. Ask Roger more about R-GRASS 7, and I think Markus will tell you. Is Markus here somewhere? Yeah, there he is. He will tell you much more tomorrow about GRASS. And computationally demanding operations are also, well, you always have to keep in mind R has never been designed as a GIS, so it wasn't designed to do large spatial data analysis. You can do it, you can also do it in the cloud and stuff like this, but then why don't use a GIS which was specifically written for doing complex, big, well, let's not say big, large data spatial analysis. And I think the most important point is R is missing literally hundreds of geo-algorithms which are available in the GIS, and as I said in the beginning, it doesn't really make sense to duplicate all the stuff that is already out there. So as long as we have an interface to a GIS, we can just use R to access GIS algorithms from other software packages. Good. There are several bridges. Today we will talk a little bit about RSAGA and RQGIS, but then there's also R-GRASS 7, as pointed out. Tomorrow you will, tomorrow or the day after? Tomorrow, yeah. You will learn more about this. And if you would like to use ArcMap, then there's also the RQGIS package. So if you are on Linux, this won't work because ArcMap is not on Linux. There are different degrees of integration. Here is an increasing degree of integration. So loose coupling would mean you just export data from a GIS and then import it in R, then do some analysis, export it back into the GIS. And the tight coupling, this is what we find here, is if you can use a GIS from within another tool, such as R or Python or whatever, or the other way around. So if you would like to use from within a GIS, R or Python or whatever programming language you would like to use. And both ways are possible. Today we will talk more about the way from within R, but it is possible. Here is an example how to use R-GRASS 7 from within GRASS. And this is also possible in QGIS. You can embed R scripts, and you can also do this in ArcMap. But as I said, we don't do this today, just that you know that this is possible if you would like to have this functionality. QGIS, why? Well, I think QGIS is one of the most popular open source software GIS packages. It is quite user-friendly. I think this is a main reason for its popularity. And it provides a unified interface. So from within QGIS, you can also access GRASS and SAGA algorithms. Not all of them, but at least half of them. So if you just want to do, or if you want many geo algorithms in one go, then you can use QGIS for this. How does it work? Like many other GIS systems, In the background, QGIS is using C and C++, and then there's a wrapper around it, Python. This is the GUI, and then you use Python to access the C++ functions, which are doing the hard geoprocessing stuff. And in QGIS, has everybody of you already used QGIS? So you know, you're a bit familiar with QGIS. You don't have to open it now. Or who has not used QGIS before? 1, 3, okay, a few persons. So later on, we will just have a quick glance at the desktop of QGIS. You can find the processing toolbox, and in this processing toolbox, there I said it before, here's Goodall, there's GRASS, there's SAGA, and you can access all these algorithms, and you can do so using Python. So within QGIS, there's a Python console, and if you would like to do not clicking, but would like to do it in a reproducible manner, then you can do it from within QGIS, also using Python. And so there is already a Python API, and what we did is just to establish a tunnel to Python via the reticulate package. And it's really interesting. We have been to ERAM in Budapest this year, and there was a talk, and it was really interesting for me to learn why reticulate was created. As reticulate lets you access Python from within R, and it was possible before. There was a package called RPython, but you could only use it under Linux, and there was no way to do it under Windows. And with the reticulate, you can do it on all major operating systems. And the reason J.J. Allaire, so the founder or chief of RStudio, has created the reticulate package, and he did this because they wanted to enable deep learning in R, or to use TensorFlow and Keras in R, and therefore they needed a Python interface, and that's the reason why they wrote the reticulate package. And, well, I use it to access QGIS. And the open app function in QGIS does all the stuff which is necessary to establish this tunnel. So it sets the environment, and it loads the necessary packages, and so on and so on. And then the tunnel is established. We can use QGIS from with R, and to find more about, find out more about available algorithms, find algorithms, and get usage, how to use one specific geoalgorithm. We will see this in the tutorial later on. Good. This was QGIS. Let's have a quick glance at SAGA. SAGA was released in 2004. This is also open source, and it started out with a focus on raster processing, so hydrology and I think also geomorphology was the main target areas in the beginning. At the moment, there are more than 600 geoalgorithms available. Okay, who has used SAGA? Okay, quite a few people. And one, I think, is it a drawback? Yeah, it is a drawback. Let's be honest. To put it mildly, the documentation of SAGA is really improvable. You could also say not existent at times. And there are the algorithms, and then you just have to figure out how to use them. It works, but on the other hand, GRASS has a really extraordinary documentation there. But well, you have to live with that. It's open source, and the algorithms are good. But well, this is a slight drawback. And there is a command line interface, and you can use SAGA from the command line, and it looks like this. You don't have to do it like this. I show this here because this is how our SAGA accesses the SAGA algorithms. It does so via the command line, via the system command. And yeah, just as a bit of background, the structure of our SAGA. The geoprocessor is well, geoprocessing environment, yeah, we need to know where SAGA is living on your computer to be able to access it. Then the geoprocessor, the RSAGA geoprocessor, is the workhorse function and provides low-level access to all SAGA GIS modules, but there are also user-level interface functions. So in the background, these functions also use the RSAGA.geoprocessor, but yeah, I think you figure out the nitty-gritty if you are really interested in RSAGA, and I will show you how to use the RSAGA geoprocessor today, and then you can just use it. Good, and there are also a few functions which are written in R, which also provide geostatistical functionality. Yeah, well, maybe a very quick glance at GRASS, first released in 1984, so it is the oldest of the oldest doesn't sound good. The most mature, maybe? Most mature GIS system from the here presented ones at least. And yeah, since 1997, the community took over and developed GRASS further. It provides more than 500 geo-algorithms as the two other software packages. It is a hybrid GIS, that means it can handle both vector and raster data. And yeah, as I said before, the documentation is spectacular. It's really great. And in the background, it uses SQLite. Or spatial light, I don't know, SQLite or spatial light? SQLite, just SQLite. Spatial light, no, interesting. Okay. But here you see there is database functionality available, so if you might need that, then GRASS would be a good choice, or one choice. PostGIS would be another. And yeah, it's a really nice interface. It consists of a lot of executables, and yeah, more or less it's a collection of many functions. But Markus will tell you about this in more detail. And if you want to know more about this, you can read our chapter on the bridges to GIS software, or if you want to more know on RQGIS, there is the R journal paper which you are invited to read. And there's also a few papers on SAGA, but I will present them later on. Yeah, we can use R as a GIS. Geoprocessing is often, not always, often better done with the help of a GIS, especially if you're missing some functionality or if you're processing large spatial data, and R-GIS bridges combine the best of two worlds. And I think that all the three packages using open source software are really good packages, and it depends always on the user which one to use. Okay, so I think now we can move on to a little example. So let's have a quick glance at QGIS and RSAGA. Again, you can find the slides and the code in our repository, geocomp.r geostats_18. And if you want to install QGIS, please follow the steps listed in our vignette. Otherwise, it is not ensured that RQGIS will work. For Windows users, I always recommend to use the OSGeo network installer, but this is also described in the vignette. You can install RQGIS using the developer version, or of course you can also use a CRAN version. And yeah, have a look at the RQGIS repository and to learn a little bit more, but I think most of the things are covered here. And we will introduce RQGIS using a really simple example. So first I use SF. Here are a few coordinates, and then I create polygons out of these coordinates, and then we have two overlapping polygons, and the first thing we would like to do, or I would like to do, is to compute the intersection. As I said, it's just a toy example. You can do it using SF as well. But to introduce how RQGIS works, I think it's a fine example. Good. So, now that I said that we would like to do an intersection, we need to find out which geo-algorithm is at our disposal. So first of all, we have to load the RQGIS library. Then the setFN function, you don't really have to do it. Sets the environment, so it looks for the QGIS installation on your computer. It's always faster to specify it if you specify the path to your QGIS installation, especially if you installed it in somewhere on your computer, which is not, I don't know. If you do, for example, some people install it on the D drive, or I don't know, then I think in this case, setenv wouldn't even find it because it just looks on the C drive for a QGIS installation. Well, and then we use the find algorithm functions and look for an algorithm which contains the word intersect. If you run find algorithms specifying nothing, then it will give back all available geo-algorithms, and I think it's more than, let's say, about 1,000 geo-algorithms. And here I use just regular expressions to search for functions which have the intersect in its name. And we will use just the first one, QGIS : intersection. But we can also use SAGA intersect. And the GRASS users, what would be the name in GRASS? Intersecting polygons. Who's a GRASS user? You are, you know. Markus? The intersection command in GRASS? V-overlay, yeah, this would be. But yeah, there are several options. But this is also, or why I'm saying this is, I have used, I looked for intersection, but yeah, in GRASS it's called overlay, so in find algorithms you won't find this. If you used overlay as a search term, then we would also come up with GRASS 7:v.overlay. Good. So now that we know how our geo-algorithm is named, we want to know which are its parameters and maybe also its default values. And for this we can use the get_usage function, and then the output is this. So we have a parameter called input, input2, we ignore this, and output. And input is just our first polygon layer, and input2 is the other polygon layer we have created, and output is the output layer, and we have to specify the path to where it should be saved. In this case, it was really simple, so because it's just 3 or 4 parameters. But if we have a look at, for example, GRASS 7:r-slope aspect, then the output is like this. And I realized, oh, nobody will ever use this package if you have to specify each single parameter. And therefore, no, in QGIS you have to do. You don't have to do it in... Well, when I started, you had to do it. It was 2 years ago, you had to specify each single parameter. Yeah, maybe. I don't know if you have to do it nowadays, but I don't care because I just collect every function parameter and the default values, and so everything is fine. Okay, no, I'm not right. It depends on how you access the QGIS API. If you use a dictionary, a Python dictionary, then it works. If you don't, it doesn't. Why ever? But this I found out just later on. Okay. Anyways, we can use get argsman to collect all function parameters and corresponding default values, and then we just have to specify the values or the parameters which are of interest to us. For example, here in this case, there are many different output rasters, but maybe we are just interested in the slope raster and not in all the curvatures and aspect things. Good. Yeah, this is the open help function can be used to access the online help of each geo algorithm, and in this case, because it's a GRASS algorithm, it just opens the GRASS help page, and as I said, it's really a good documentation. But let's get back to our use case. Remember, we created these two polygons and we wanted to find the intersection. We already found out that we need to specify these parameters, and yeah, then let's do it. We can just use R-named arguments, so we know how the parameters are called, and then we just type it in like this. So input is our poly1, and as you remember, this is an SF object living in our globals environment. You can do this in RQGIS. Then we have input 2, this is our polygon 2, and we also specify the output path here, so we would like to write the output to a file named out.shape. And if we also say load output equals true, then the QGIS output will automatically be loaded back into R. And I save it in an object named int, short for intersection. Okay, and yeah, this is the result. So I plot the two polygons, and then finally I also plot int, and this is our intersection. So, if you want to know more, have a look at these references. Anita Grasser and Victor Olaya also wrote a nice paper on the QGIS architecture. Good. Let's have a short look at SAGA as well. And we will do the exact same example, just in this case we're using the RSAGA interface. So first of all, we have to load the RSAGA library, then we use rsaga.env to set the environment, and SAGA or rsaga.env will also automatically look for a SAGA installation, but if you have installed it in a funny place, it won't find it, and then you have to specify the path argument. So you say here in this place, my SAGA is living. Good. After we have done that, we also have to find out what are the names of the different libraries and of the different geo algorithms in each library. And RSAGA get libraries will tell you more about it. And I just give back here all libraries which have shapes in it, or the word shapes, because we want to do an intersection of polygons, so these are shapes. Shapes, yeah. Vector layers. And here we see, okay, there's shapes, polygons. I guess we will find our intersection function there, and using the get modules command here, it will give back all geo algorithms which are available in this module. And in this case here, there is an intersect function. And again, we need to find out how to use it, and we use the rsaga.get.usage function to specify the library and the geo algorithms, and then we retrieve this output. And now we know that we have a parameter called A and B and result, and we need to specify these parameters. In RSAGA, it's not possible to use SF objects, so we have to first export our polygons, and I do this using the write_sf function, and I save them to a temporary directory, and then we can finally run our geoprocessing workhorse, the rsaga.geoprocessor function. And again, we have to say, okay, this is our library, and this is the name of the geo algorithms we would like to use, and then we have to specify the parameters via a list. And in the list, we have to use the parameter names we have found out here. Okay, so I say A is file 1, B is file 2, then I also say save it in this directory, and the split thing is for, let me think, what's the name for it? If you have a polygon and another polygon and they belong together, multipart polygons. So you set it to false if you would like to keep multipart polygons. Good, and then that's it. Then we can also load it, or we can load the output back into R using the st_read function, and this is the result, the exact same result as we have seen before. Yeah, have a look at the RSAGA vignette for a deeper look at RSAGA. There's also a nice paper from Olaf Conrad et al. Olaf Conrad is the main maintainer of the SAGA GIS software, and you can also read a bit more about this in our R-GIS Bridges chapter. And now I would suggest that you just run the code or have a look at the code. And then there are also a few exercises, and what's the time? Yeah, I think you can have a look at this for 10 or 15 minutes, and if you have any questions, just ask me. You find the code again in our geostats_18 repository, and the code is here. And yeah, have a look at it, and if you have any questions, feel free to ask. The link again, it's here. So it's github.com/geocompr/geostat_18, and then there is code and R-GIS bridges, and there you find the QGIS intro. And this just reproduces the stuff I have just told you about. And then you can go on and try to solve the few exercises you can find here. And if you have any questions, just let me know. And then I think in 10 to 15 minutes, I would like to do something else, because in the next session, we will talk about spatial cross-validation, so modeling stuff. And for this, we need spatial predictors, and we will use RQGIS to create our predictor rasters. But we will do this together. Yeah, I didn't mention today, but at the moment, RQGIS is only supporting QGIS 2.18. That is the long-term release. I said so in the post, in the software requirements, but maybe I should have said it again. QGIS or RQGIS already works with QGIS 3, but I still have to do some fine-tuning, so it will take me a couple of, let's say, months, because at the moment there's so many other stuff to do. But it will work in the near future. Yes, and now I just would like to present how to use these bridges to derive predictors from a digital elevation model. So let's see, and this is a code session, so we will just go together through the code. Let's just start with a new our session. So I attach several packages, RQGIS, SF, raster, and dplyr. And then in the QGIS package, you find a few data sets, and I load them into the workspace. So this is random points, and random points, well, we will see them in a moment. And then there is DEM, NDVI, and the study area. Yeah, let's have a short glance at the data. So this is our study area, and we have sampled there. Well, I'll tell you more about this later on. Here, this is just the DEM, and we want to extract a few predictors from this DEM, and before we do that, I just remove some artificial sinks which can occur with digital elevation models, and for this, we are using a function called SAGA::sink removal. And again, we can find out how to use it using the getUsage function, and you see there are several parameters which can be specified. And if we run getargsman, then all the parameters will be put in a list, and if there is a default value, then it will be the list element. So, for example, there should be, for example, here, the method is the parameter and the argument is 0. Good. If you would like to run the SAGA::sink removal, we have to define the input DEM, then the method, I say fill sinks, this is the method 1, and then we have to tell RQGIS where to save the output, or better said, we have to tell QGIS where to save the output. So we run this, and then we get this result. And next, we would like to compute as predictors the catchment slope and the catchment area, and we can do so using the SAGA wetness index. You can also calculate the SAGA wetness index with this as well. If we would like to know how to use it, we have again a look at this getUsage stuff. Then we will find again several parameters which can be specified, and here also the options are displayed. So, for example, here's area type, and you can specify for area 0, 1, or 2, and 0 corresponds to the absolute catchment area, 1 to the square root of the catchment area, and so on. And it depends what you would like to have. We would like to use the absolute catchment area. And slope type equals 1 is the catchment slope. These are the two values or rasters we would like to calculate. And we can then run QGIS by specifying again the algorithm. Then we say DEM is our input raster. We say we would like to calculate the catchment slope, and we would like to calculate the absolute catchment area, and then we also have to specify the output paths. I call them here cslope.tif and carrier.tif. So cslope for catchment slope and carea for catchment area. Maybe on the Windows you have to replace this .tif by .sdat. SDAT is a SAGA raster format. Good. Yeah, let's run it. And all the files are saved here into this folder, so they are at your disposal as well. So if you clone the repository, you already have all these files, so you can run the subsequent analysis as well, even so if it was not possible for you to run the RQGIS commands. And now that we have retrieved our predictors, we all put them into a raster stack. So in the stack, I put the DEM, I put NDVI. NDVI is also the normalized difference vegetation index, and it also came with the RQGIS package. So we can also plot it, that you see this is the NDVI here. And so I put into the raster stack the DEM, the NDVI, and then our recently calculated predictor variables, that is the catchment slope and the catchment area. Yeah, let's do this. And after we have done that, yeah, let's have a look at the distribution, and we see that the catchment area is highly skewed to the left. And yeah, if you're using machine learning, maybe, I don't know, you don't have to normalize things, but old habits die hard, so I just normalize stuff. And if you now look at the catchment area, it became more normal. And finally, we would like to extract all these values to our random points. And the random points, this is an SF object, consists of 86 observations. We can also plot it. And these are the points which we visited in the field, and now we just extract the values to these points, and we can use the raster extract function for this. And it's really pretty because we just give it a raster stack, and we also say use random points, and then all the layers in the raster stack. So if we have a look at TA, then you see there is DEM, there's NDVI, there's catchment slope, and there's catchment area, and all the values will be put to the random points. So before we do that, let's have a look at random points. So far it consists of 3 columns, ID, species richness, and geometry, and now we add 4 further columns. So we extract the NDVI, the altitude, catchment area, and catchment slope to these points. So if you look again at these points now, we say that we have extracted the values, and then we save these values, and then we can go on to model our floristic gradient, but we will do this after the break. So now any questions, comments? So if not, I would propose we have coffee now, and then after the break we will do the spatial cross-validation thing, and we need this stuff we have done here as input for this spatial cross-validation. Okay, so see you in a bit.